Hassler here. I'm going to do notes on 5.2. We are starting to look at some more advanced applications of derivatives. So we are going to look at extrema. When we talk about extrema, we're talking about extreme values. Extreme values are points such as minimums and maximums. So when I talk about absolute or relative extrema values, I'm looking at absolute minimums and absolute maximums. All right, so it says label each graph. I'm just going to go ahead and do that. To me, it looks like this graph is cut off. So this to me would be, I'll just call this point A, and this would be an absolute minimum. Absolute means it is the lowest point for the entire graph versus this endpoint up here, and I'll call that, let's see, we'll call this B, C, D, and E. And this would actually just end up being a relative or a local min. So I'll say relative min. It's a low point locally. In that general area, it's a low point, but it is not the lowest point. So that would be the difference between an absolute and a relative or local minimum. Another relative or local minimum I have here is point C. And so again, I'll just abbreviate due to space, relative min. This is a low point in this general area, but it is not the lowest point. When I take a look at this second point here, I'll call it point B. I would call this a relative or local max. It's a high point, but it is not the highest point. So in the general area, it's the highest point, but it's not the overall highest. So A, B, C, D, and this would be an absolute max. Not only is it locally the highest point, but it is also overall for the entire graph, it is absolutely the highest point. Okay. And so let's come over here and take a look at this second graph. In this second graph, this would be an absolute max. This is the highest point for my graph. And it looks like this right here would be an absolute min. The problem is that it's an open circle. It's not defined. For that reason, I can't say that this is the lowest point. I don't have a defined lowest point. When we're talking about these absolute mins and maxes, we're talking about the y values. And so you might say, well, yeah, the lowest point is at -3. I'm not defined at -3, so we could argue maybe -2.9. But if I argue -2.9, somebody out there is going to argue, yeah, but -2.99 is even lower. And I'm going to say, oh, you're right. So -2.999 is even lower. You get the idea. And so this is nothing. This is not an absolute min. This is not a local min. It's none of those things. It has to be defined in order to be considered a minimum or maximum. With that being said, this right here would be considered a relative max for this general area that is a highest point. And this endpoint here we could say is a relative min for this general area. It is a low point. And again, this over here, this endpoint is none. I can't say anything about it because it is not even defined. So some things that I notice, and this is actually coming from the Desmos that you should have worked through. Things that I notice is that when I'm talking about slopes, I notice that anytime I have this relative max or this relative min or this absolute max, the slope of the tangent line to those points is 0. So we can say a minimum or maximum value for f of x has a derivative that equals 0 or I notice here that I have an absolute max and that derivative would not be 0. I actually cannot draw a tangent line there. And we talked before that I'm not differentiable here. So it still happens to be an absolute max. So f of x either has a derivative that's equal to 0 or a derivative that does not exist. And I'm just going to abbreviate that does not exist. Or is at an endpoint. That's going to be also very important in the upcoming units. Okay. And then based on the Desmos, you looked at where the derivative or the slope of the tangent line could be positive or could be negative. And we'll get more into that in sections 5.3 and 5.4. All right, so I want to define what a maximum and minimum really are, tell you what absolute or local relative extrema are, and then I'm going to do a couple examples. Yeah, we'll go with pink. So maximum means that f of c is a maximum value. By the way, when we talk about min and max values, it's a y value. F of c is the output at c. So is a maximum value of f of x if and only if f of c, the output at a specific x value, is greater than or equal to all of the other outputs for all x in the domain of f of x. In other words, this y value has to be bigger than every other y value. If that's true, this y value is bigger than every other y value, then that y value is the maximum. It's the highest point. Absolute means that it's the largest function value. I'm going to say y value because, again, mins and maxes are related to y value, so it's the largest y value over the domain of f of x. Versus a local or relative maximum is the largest y value or largest function value. We say in the neighborhood of the domain, meaning for that small section. So when I come back up here to a relative max, in this neighborhood, this small area that I'm looking at, that y value is the highest y value. Versus this up here, this absolute max, is the highest over the entire stretch of the function. Okay? So when I say neighborhood, I just mean for that small section. All right, so let's go back and look at minimum. We will say something similar. We will say f of c. The y value at c is a minimum value, again, a y value, a minimum value of f of x if and only if f of c, the output at c, is less than or equal to all of the other y values for all x in the domain of f of x. Again, what that means is that if this output at c, if that output is smaller than every other y value, then that output is a minimum. Okay, seems reasonable. Absolute, again, would be the, not the largest, it would be the smallest. If we're talking about an absolute min, this would be the smallest y value on the domain of f of x. And if I'm talking local, then I'm saying it's the smallest y value in the neighborhood. Of the domain of f of x. Okay. So that's part one. Part one is just being able to look and identify where a function has a relative min, a relative max versus an absolute min or an absolute max. That can happen at the endpoints. or it can happen at corners like in my second graph. The second part of this is looking to find the x value in which the derivative is 0. And so the second part is looking at this. Finding the x value where a derivative is 0 or where a derivative does not exist to tell me where I would have a minimum or maximum value, the location of that minimum or maximum value, okay? And so we're finding and identifying critical points. A critical point is a point on the graph of f of x when the derivative, so I'm going to say when f prime of x equals 0 or when f prime of x does not exist. And what happens is that you have either a min or a max at that x value of that critical point. Okay? And so, great. What that means is I got to find when the derivative is 0 or when the derivative does not exist. Well, I know how to do that. I know how to find the derivative, so I'm going to do that. F prime of x equals, and the derivative would be, well, power rule says 3 times a third is 1, so x squared minus 9. And then I want to find when this derivative is equal to 0 or when the derivative does not exist. That means I'm looking for when this function, this derivative function, is 0. Well, I can do that. I'm going to find when x squared minus 9 equals 0. You must write that you're finding the x values when this derivative is 0. If you don't write that, I'm dinging you for notation. And AP will as well. I can set each factor equal to 0. A little bit of algebra here, and I can solve, right? So either x is 3. When x is 3, I have a derivative of 0. Or x is negative 3. When x is negative 3, I have a derivative of 0. And actually, I want to go to Desmos, and I want to graph this for you. So I'm going to graph the original function, hopefully here. And when I graph this original function, what do I have? I have y equals 1/3 x cubed. Oops, sorry. Gotta get out of there. X. We're starting over. All right, we've got y equals 1/3, arrow out, there we go, x to the third. And then I have minus 9x, and I have plus 24. And so when I take a look at this graph, I notice that when x is equal to 3, I have a minimum. And when x is equal to, gotta go all the way up here, when x is equal to negative 3, I have a maximum. So that's what I'm finding. At a min or a max, this derivative is 0. The slope of the tangent line to this function f is 0. And I'm able to find algebraically the x values where that occurs. Algebraically, I found that that occurs for f at an x value of 3 and an x value of negative 3, okay? Or I can look to see when the derivative does not exist. The thing is, though, that's not going to be the case for a quadratic. Never the case. There's no value of x where my derivative doesn't exist because there are no vertical asymptotes, there are no holes, there are no corners when it comes to a quadratic function, okay? And so I don't have to worry about that part when it comes to a polynomial. Well, let's take a look at problem 2. So in problem 2, again, I want to find when the derivative is 0 or does not exist, so I have to find the derivative. But in order to find this derivative, I'm going to first rewrite this as 4 minus x squared to the negative half. All right, so I'm going to find this derivative, g prime of x equals, drop my negative 1/2 down, gum stays inside, to the negative 3/2 times my gum. All right, and so what I really have here is I really have a negative half times negative 2. Those actually undo each other. And so when I go to rewrite this, I still have an x in the numerator, right? but I've got to move this down to the denominator. I'm going to write that as the square root of 4 minus x squared, but all of that is being cubed, right? Because I'm to the 3/2. And now I got to figure out when does this equal 0 or when does it not exist, all right? And so here's the deal. This function is equal to 0 when the numerator equals 0. Think about it. 0 divided by anything gives me 0. So if x is equal to 0, I'll do that in black. If x is equal to 0, then this whole fraction equals 0. 0 divided by anything is 0, okay? Now, I also need to determine when does this not exist. So when does g prime of x not exist? Well, it's not going to exist if my denominator is equal to 0. If my denominator is equal to 0, then the overall function doesn't exist because I'm not allowed to divide by 0. So now I got to find the x that would make the denominator be equal to 0. This is that whole domain restriction thing that we did back in, I think it was unit 2 or something. And so let me see. I'm going to go ahead and start solving for x. So I got to cube root both sides. Well, if I cube root 0, it's still 0. And then I got to get rid of, so I got rid of the cube. I got to square both sides to get rid of the square root. And if I cube root and square 0, I still get 0. So I have 0 equals 4 minus x squared. I'm going to add x squared to both sides, and I'm going to take the square root. I get plus or minus 2. So it's possible that at positive 2 or negative 2, I also have a potential min or max. So at 0, I have a potential min or max. At 2 or negative 2, I have a potential min or max. But we have to be careful. We have to make sure that anything that we find that would cause the derivative to be undefined would not also cause the original to be undefined. So if I were to put this into the original function, my original function is not defined. So this also makes g of x undefined. Which means I was not even allowed to take the derivative anyways. At x equals plus or minus 2. Let me show you what that means. So let me attempt to do this here in Desmos. All right. So let's see. We've got y equals, I've got 1 divided by, and then I have the square root of 4 minus x squared. Enter. All right, and I'm going to hit home, get me back here. So here's what's happening. We found that we have a critical value or potential min or max here at 0. We said when x is equal to 0, the whole derivative equals 0. So that checks out. What I noticed, though, in the original function here is that it almost feels like I have these vertical asymptotes happening here. My function clearly is going vertical against negative 2 and 2. You cannot take the derivative at a vertical asymptote. So can't take derivative, at a vertical asymptote. And so that's why it wouldn't even make sense to say I could have a potential min or max at 2 or negative 2 because that function is just going to keep heading towards infinity in both directions. There are just some things like that that you need to look out for. All right. So with all that knowledge that you now have, your job is to attempt the practice. In 1, 2, and 3, you are going to do things like identify the type of extreme value and where they occur. For example, an answer could be written as absolute max of 3 at x equals 1. Here, I'll do this first one with you. And so I would say, looking at this graph, that I have a, well, I can't count this one. That's not a min or a max because it's not defined. But I can count this one. So it looks like I have a relative max at x equals -2, I should do what they did. Let me do this. I could say here, I've got a relative max of, that's my y value, -1 at x equals -2. And that would be this here. So you're going to do that you're going to identify all of the mins and maxes for each graph and say what they are and where they are. When it comes to 4, 5, 6, 7, 8, 9, you're going to do your very best. You're going to find the critical points by finding the derivative. And then after you find the derivative, you're going to see where it's equal to 0 or where that derivative does not exist. Okay? Algebra. All right, we'll talk in class the next time I see you about how this went. Ask me questions if you have any.